All right, so as I mentioned last time, so I hope to use this lecture to review what we have covered and give you a chance to ask questions. So it's like a combination of a lecture, review lecture, and an office hour. Hopefully, I can provide more high-level understanding about what we did and to give you more insights into those methods. So first of all, this is what we briefly stopped at the end of our last lecture. So just to give you a basic idea of what we did, just quickly go back to here. Let me see. Okay. Okay, so I will go back to this formulation here. So the last part of our lecture, though brief, we covered the linear mixed model. So the most general form of the linear mixed model can be written in this way. This is the fixed effect part, and we call X as the fixed effect design matrix. Here, we put the covariates whose effects, the effect sizes, I should say, the effect sizes or the slopes we are interested in estimating into X. And their slopes or coefficients are beta. We want to estimate. This is the fixed effect part. And when we say it's a linear mixed model, we mean it's a mix of fixed effect and random effects. So the random effects go here. And we have a random design matrix, random effect design matrix, which will include the random effect covariance. In most cases, the random effect only includes intercept. It's like a random intercept model. But in some cases, you may want to consider random slopes. For example, if there's one slope per group and you have many groups, so you are not interested in the group specific slope, but you are interested in the between group variance of those slopes. Then you put those slopes into this Z, input the group into Z. So in this case, you would have basically a group indicator, which will indicate the group you have in, and then you will have the covariate whose random slope you are interested in estimating. So delta would again contain the slopes of the random effect covariate. But the difference is that for delta, we don't want to estimate them per se. We only want to estimate the variance of the different components of delta. So we basically estimate the variance component instead of their values. And epsilon is the random error. So then this is the most general matrix form. And putting things together, essentially, we want to assume that the two random things, one is epsilon, one is delta, a linear mixed model jointly follow a multivariate normal distribution. So zero mean and the covariance matrix of error vectors R, and the covariance matrix of delta is denoted as G. This is the most general notation you will see in linear mixed model papers and textbooks. So I'm just going to this most general form. And the previous examples we gave you are special cases of this. So last time we spent quite some time to talk about the stacking, if you remember, like the stacking. So we have, say, n small n groups. Each group has sample size small ni, and the sum of small ni is big N, right? Remember, we talked about this stacking. So X design matrix, let me just finish this. So the X design matrix is n by p, big N by p after stacking all the groups together. Z is big N by small n times R. R is the number of columns of the random design matrix, N is number of groups. So correspondingly, delta has NR by 1. So there are R parameters for each group, and we have a total of small n groups. So that becomes NR. Okay, so using this joint notation, we will have this joint multivariate Gaussian distribution. And previously, we said that the epsilon, we have small n epsilon. So basically, I just write one more thing, epsilon 1 to epsilon n, okay? And epsilon I is ni dimensional. That's how we derive this. So therefore, each epsilon I, if assume it has a covariance matrix sigma I, then putting them together, they are independent among the n groups. I have sigma 1 to sigma n. And this portion, which is n by n, is now denoted as R. Okay, and this portion from delta, we said that each delta I, so again, delta has n R by 1, right? We have delta 1 to delta n, and each delta I is R dimensional. So each delta I has covariance matrix omega. That's what we did last time. So omega is R by R, then putting them together, I have NR by NR. So therefore, R is referring to this N by big N matrix, and G refers to this NR by NR matrix. So that's how we get G and R from the previous lecture. Okay, but this is not so important for the detail. I mean, the high level understanding is more important. So we have a variance component for the error term, random error. We have a variance component for the random coefficients, the delta. And what we aim to estimate is not the delta itself, but the G and the R. So with R and G, we can basically write the model as this. We can put all the components, look at this model 3. We can put all the random components into one general term. We can call that epsilon star. So therefore, in this model, we have a fixed effect and random effect. Random effect contains both the random effect we are interested in and the random error. So in this way, it becomes just like a linear model. It's just that for the random part, we can further decompose it as epsilon star can be further written as z delta plus epsilon. Okay, so then, assuming delta and epsilon are independent, we can decompose this covariance matrix of epsilon star as big N by big N by doing this decomposition based on the independence, okay? This is what we mentioned. When the two things that add up are independent, then the covariance of their sum can be written as the sum of their covariance matrices. So we have this plus this, and then we can apply the fact that the design matrix is fixed. So we can get it out of the covariance. So we can write as Z times the covariance matrix of delta times Z transpose. Finally, this is what we get. Okay, so basically the randomness of epsilon star, the variance covariance matrix of epsilon star can be written as Z times G times Z transpose plus R. G is the covariance matrix of delta. R is the covariance matrix of epsilon. This is the most general form of linear mixed model. Okay, so you see that with this, then let me go to this page. Okay, it's the same thing here. I basically can say, okay, this is my model, but this error vector is following an n by n, it's following an n-dimensional Gaussian distribution with a covariance matrix written as V. So V is this V. V is Z times G times Z transpose plus R. So why do we have this V written as theta? What does it mean? Here, the theta are just all the parameters we need to estimate. So V is just a general term. So if we go back to a more specific example, let me see. Okay, in a more specific example, we basically said, okay, right here. So going back here, if you believe that your epsilon I, this ni-dimensional vector, this corresponding covariance matrix called sigma I, is just a diagonal matrix with just one term sigma squared, then that sigma square will enter your parameter theta to be estimated. So there's one variance term with error term that can be written as sigma square. Then for this omega, and the omega is the, let me just write this here. So epsilon I, the covariance matrix, is written as sigma I, and we can simplify this as sigma square. Okay, Ni by Ni. So then you have only one parameter to estimate in this very general or commonly used simpler form. Then we have this covariance matrix of delta I, which is R by R. We specify this to be omega. Okay, and for this R by R matrix, we can also simplify it depending on whether you think the R dimensions, the R coefficients in sigma I have any dependence, have any correlation or not. If not, you can further simplify this as omega squared R by R. If you do this simplification, then your variance component parameters are just two, just a sigma square and omega square. And that's what you call as the sigma. This is just a simple case. And you can make it more complicated. For example, if you want to introduce some dependence covariance structure in this R by R matrix, that these things will enter the sigma. But I would say in most cases, people use its sigma is not so complicated. It's just the parameters you need in the variance components. Okay, so if we have this formulation, then the parameters we need to estimate in this linear mixed model will be two things. One is this theta, one is this sigma. If you can estimate both, then you have the model estimated. Does that make sense? Okay, so therefore, the question, which we briefly touched but didn't detail, is how do we estimate sigma? How do we estimate theta? Because beta is not so challenging. Once we know theta, beta still takes this form we are familiar with, like the least square formula. So it's just like the weighted least square. So because we have the I shouldn't say error, I have the random part following normal distribution with this covariance matrix, then just like the weighted least square, this covariance matrix will enter our least square formula. So V theta inverse, they need to appear here, but they depend on theta. If you don't know theta, you cannot use this formula to get beta hat. So beta hat depends on theta. Then how do we estimate theta? There are two ways. One way is that you directly do maximum likelihood estimation. That is, your likelihood would involve beta and theta. You first fix theta, find the corresponding beta hat MLE, then you put this beta hat MLE into your likelihood. So then this becomes a parameter depending on theta. This is theta. So the only parameter left in your likelihood is theta. And this is called profile likelihood. Then you can do some optimization to find the maximizer. Another way is that you want to estimate theta alone. Then you want to get rid of beta in the likelihood. Then you can do integration over possible values of beta to get rid of beta. And this is called marginal likelihood of theta. So this is not a real likelihood because beta is the parameter you don't know. But here you are just integrating it out without worrying about it. Then this marginal likelihood of theta, we can use the property for integration for this Gaussian-like function using the property that the Gaussian density integrates to 1. Then you can solve this integral, and finally, you can show that there is a relationship between marginal likelihood of theta and the profile likelihood of theta, which actually is this. On the log scale, log marginal likelihood of theta is equal to log profile likelihood of theta minus this term that involves theta. Okay, so then if we want to find the maximizer of the marginal likelihood and call that an estimator of theta, it is called restricted maximum likelihood, REML estimator. So in this linear mixed model literature, we have two estimators of theta. One is restricted ML, REML. The other is the real ML. Okay, so they are not equal to each other, but they have some different properties that we may use one or the other. I made a mistake last time, but I want to correct it. I want to say that basically the marginal likelihood estimator, the REML estimator, can be shown as unbiased for theta given a finite sample. So it's not just asymptotically unbiased, because the ML, this one, the theta ML, if we just use the profile likelihood to get the theta hat, it is asymptotically unbiased, but it's not finite sample unbiased. So what is the difference? You can think about the difference as when we have just 1 over n variance estimator versus the 1 over n minus 1 variance estimator. It's very similar. So this is what we know as the ML. This is actually the variance estimator by maximizing the likelihood. You would have 1 over n. You would divide n. But we know this is not unbiased as a finite sample. So the bias for this one is actually on the order of 1 over n. So you actually have this bias, but this bias is going down to 0. So that's why we say it's asymptotically unbiased. But this one is unbiased. You see, the biggest difference is that when you divide by n minus 1, you account for one thing. That is, you lose 1 degree of freedom for estimating the mean as y bar. So when you do the mean estimation, you lose this degree of freedom. But if you know the mean, if you know the population mean mu, then if you do 1 over n yi minus mu squared, use this as the estimator of the variance, then this becomes unbiased. So dividing by n here is okay because there's no mean for you to estimate. But on the left-hand side, when you need to estimate mu as y bar, then you need to account for the loss of the degree of freedom. Okay, this is the same thing as we have here. So when we use the profile likelihood to find the maximizer and call that theta hat ML, what we ignore here is that the beta hat are to be estimated, and we will lose some degrees of freedom for estimating the fixed effect, the beta. While if we go to the marginal likelihood here, beta is totally gone. We don't need to estimate them anymore. We're only left to estimate the theta. So it's kind of like we're doing the n minus 1. So we're basically removing the degrees of freedom so we are accounting for the lost degrees of freedom implicitly in this approach, which is kind of interesting. And also, one more thing to say is that there's an equivalence to show that if you do this marginal likelihood derivation, it is equivalent to the likelihood of what? To the likelihood you derived using residuals, y residuals instead of y. So what you can do is that you first fit a linear model and you get y hat. So you ignore the fixed mix effect, you ignore the random effect. You just fit a linear model with your fixed effect covariance, your design matrix X. You get y hat. Then you do y minus y hat to get your residuals. And then you assume that your residual follows this distribution, normal distribution with covariance matrix V theta. Then you use your residuals and this distribution to write down the likelihood of theta. That is exactly what you will get for this marginal likelihood, which is very interesting. So basically, in that way, when you derive the residual, you already accounted for the loss of degrees of freedom. And then that will make your theta hat REML unbiased. Okay, so that's a very high level explanation of what is the difference between this theta hat REML and theta hat ML. In short, theta hat REML is unbiased, just like this n-1 estimator, while theta hat ML is biased, just like the 1/n estimator. And when do we use each? That's the question. When do we want to use the REML and when do we want to use the ML? So if you go to the R function, the R package for linear mixed model, the LME4 package, and there's a function called LME function, you should be able to specify REML or ML for theta estimation for the variance component. And when do you want to use each? Okay, the question is, what do you want? So basically, if you want to test whether the random effect is 0, if that's your question. So basically, if your goal is to know whether the random effect covariance you put into Z, does their random effect matter or not? If that's your question, you should go with REML because you care about the random component. And I think the unbiased estimator is better. But if you are interested in testing the fixed effect, okay, if that's what you're interested in, then you want to use the ML. So if you're interested in beta, because in that case, you would just use likelihood, the full likelihood, and do a likelihood ratio test to compare two models. Say one with a fixed effect set to 0, the other with a fixed effect be free. Then you can do the likelihood ratio test. And then the likelihoods, the two likelihoods must include your beta, right? So you must go with a full likelihood, not just the marginal likelihood for theta. So you will use ML. So basically the goal is whether you're interested in fixed effect or random effect. Okay, and in many cases, we use random effect just to make sure that we have a better estimation for the random error variance, the variance of epsilon, because that's what will affect our beta hat, how confident we are for our beta hat. That's still our fixed effect is our interest. But sometimes we want to say, for example, in the education example, if we want to say, oh, does school matter in determining students' performance? Like whether the schools do have very different intercepts, different baselines. In that case, we're essentially interested in testing whether the variance component is 0, whether the schools do make a difference, even though we don't want to get a school-specific effect. So that's two types of questions. They can both be answered by linear mixed model. Okay. All right, I think that basically wrapped up what I want to say, but didn't have time to say about the linear mixed model. I acknowledge that we have encountered several challenges this quarter, which kind of delayed our progress as usual, but hopefully you still have a high level understanding of the linear mixed model. Because I think for this part, you will mostly relying on existing package for doing the parameter estimation. But the most important thing is whether you are able to interpret the output from the method, from the R package, know what they actually mean. Okay, so I think that's all about the linear mixed model. So then for the review part, I hope to do the following. So first of all, I want to say that the core of this class is we want to link our response yi to some covariates, which we call xi. So their relationship is what we are ultimately interested in. And in this relationship, there is a direction. We want to see how well can the covariates predict the yi. Okay, so there's a directional effect. And also we have to bear in mind that there are some random errors or randomness that cannot be explained by covariance. Okay, so we have some unexplained part in our yi, and we call that randomness. So basically, something we have to think about or we have to remember is that whenever we talk about randomness or whenever we talk about random variables, we are making assumptions. Okay, random variable is our assumption because the data we see are just numbers. And we are making some thought experiments by imagining that they're random. That is the fundamental part in statistical modeling. Okay, we use randomness to describe the things we cannot fully predict, basically. Okay, so then, because of this, the core of this class is that we have the model written as a random structure, which we said again and again, and the systematic structure. So for the random structure, what we want to say is that, oh, the things we can predict from covariance is what we think as the signal or the true value or the mean of yi. And we call that μi. So specifically, we assume that yi are independently following some distribution. And in particular, we focus on exponential family distribution with this mean parameter μi for observation I and some other parameters we need to account for. Let me just codify. And just make sure that we have made two assumptions. One is that the distribution is exponential family. The other is independence. Independence is crucial. It means that we believe the variance or the variation we cannot explain, which is considered to be yi is different from μi, right? That difference is considered to be random. And we assume that difference to be independently random for different i's. That's a very crucial assumption. Okay, independence means that, okay, this yi may be bigger than μi or smaller than μi, but this doesn't tell me anything about another, say, yj, whether it's bigger than μj or smaller than μj. I cannot say anything. Okay, that's the random part, unexplained part. The systematic structure is what we will use for prediction. It is how we are going to link μi to xi. So depending on the form of the random structure exponential family, because μi may be between 0 and 1, like a probability, or μi may be positive. So, but xi can take real values. So therefore, we need some transformation of μi to be reasonable. So they can be a linear function of xi. So therefore, we write g of μi being xi transpose beta. So this is the linear part. So we always have a linear function of xi. But this part, g, will depend on the random structure. And this is called a link function. And in this class, we also give this g of μi a notation as eta I. You have seen this, and eta I also has its name called linear predictor. This notation eta is just introduced for convenience, nothing else. Okay, so this is what we have spent quite some time on, and it's called generalized linear model. The generalization happens in two layers. One is that the exponential family is a generalization of normal distribution, and the link function is a generalization of the identity function. So both are used in the normal linear model. Okay, so the reason we do this is just to account for that the data yi may not look like normal random variable or Gaussian random variable. So therefore, if it's count data, Poisson is commonly used to assume some randomness, right? Because given the same Poisson mean, if you draw different times independently, you may get a different count. And that is the randomness we're talking about. And we can also generalize Poisson further to negative binomial to account for over dispersion. That is, the variance may be bigger than the mean. You may even account for zero inflation by going to the hurdle model or the zero inflated model, right? So you can get a model more complicated. And for the systematic structure, we said that for exponential family, there's a canonical link function, right? Basically, that can directly link this to that location parameter in your exponential family. And you can also have other non-canonical link functions which was historically used but may not be so popular nowadays given the generalized linear model GLM theory prefers to use the canonical link function for simplicity. And then for the optimization that we aim to estimate model parameters, this is the key. What is the parameter we want to estimate? Beta. Beta is the most important thing because it's how we can interpret the model. We want to use beta to say, okay, this covariate, if we change it by 1 unit, how it can affect the mu I, right? And mu I is the mean, the signal we are looking for yi. So we can have some interpretability by looking at the beta. So we want to estimate beta for sure. And phi, this thing in statistics is often called nuisance parameter because it's not a thing we are interested in, but we must estimate because we don't know it. So therefore, like the negative binomial dispersion or in Gaussian distribution, the variance are both such nuisance parameters we must estimate. But our parameter of interest is always beta. Okay, so far all this discussion is about fixed effect. There's no random effect involved at all. Any questions before we move on to the random effect? So I hope to give this very high-level summary about what the generalized linear model is doing. And for that, the linear model is just a special case. And also different from machine learning algorithms, which are strong in prediction. The strength here is interpretability. So we have this beta to interpret. And sometimes this model may fit very well to data. So if it fits well to data and it's interpretable, then it's ideal. So then my question for you is, how would you possibly check the model fit? Goodness of fit of the model. This is something we talked about in the class. Do you still remember? The goodness of fit test.
I think so there are t-test, ANOVA test, and f-test, something like that.
Which one would you use for goodness of fit? Actually, there are multiple options. Yeah.
Yeah, I probably use like a likelihood ratio test.
Yes, likelihood ratio test. And there is a test statistic associated with the likelihood ratio test called the deviance, right, for GLM. And what it actually does is that it compares this GLM model to the saturated model. And the saturated model is where each yi is its own mu I hat. We use the yi to estimate mu I. So that's the, overfit, I would say. Basically, we just overfit the data, right, and call that a model. So we're comparing this GLM to that model to see whether the goodness of fit has some obvious difference. If not, or significant difference. If not, then we will go with the GLM. Okay, so I think this idea is very, very important to check, because otherwise, if you just say, oh, I'll assume this model, but you can assume any model, and some model may be reasonable, some may be unreasonable. So checking the goodness of fit is very, very, very important, I would say. But now I would say there's a simpler way to do that, even though you don't know so much about statistics, which I think is useful for practice, and it's something I'm advocating for my research. That is, you can sample from this fitted model. Suppose that you fit a GLM and you have the beta hat, and correspondingly you have the mu I hat. You also have the nuisance parameter estimated. So given all those parameters estimated, what you can do is that given each covariate xi, I can sample the yi from this fitted distribution. Then I can have this sample data, you can call it synthetic data or whatever. Then you can compare the sample you draw from the fitted model with your real data, with the original data. And you can compare their distributions, you can compare their different aspects to see whether they are indeed similar. I think this is a very useful check because if the model does fit well to your real data, then the sampled synthetic data should be similar. Otherwise, the model doesn't fit well. Okay, so this is something I will encourage people to check. And especially if you have a more and more complicated model, then the goodness of fit test may not be easy to implement, or you may not easily write down the likelihood, but sampling is much easier. So that's what I think as a useful practical strategy for checking the model goodness of fit. All right, finally, so with that, we want to use the beta hat to do some inference about beta. And the inference means that typically hypothesis test or confidence intervals, because we're just talking about the frequentist idea in this class. So when we say hypothesis test, we have a null hypothesis that some coefficients in the beta might be 0, because we're interested in whether the corresponding covariates have effects or not on the mu I, on determining the mean of the response. So then null hypothesis is to set those beta j to 0, and then we can use the beta hat j to get a test statistic to test the null hypothesis. Now, typically, if we have just one beta j of interest, we will do a t statistic, right? We will standardize the beta j hat by its standard error, and then we will get a t statistic. That's the standard practice strategy. If we want to test multiple components of beta, whether they're jointly 0 or not, we can do a wall test. Or we can have another strategy, that is we can do a likelihood ratio test, right? Or ANOVA. So for a linear model, we have all these options. But I think for generalized linear model, we typically just use wall test or likelihood ratio test. And there's another category of test which I didn't talk about in detail, but I mentioned in one of the lectures. It's called a score test. The score test is another way that's based on the score, which is the gradient of the log likelihood. We can also construct a statistic because we know that under the null model, the score statistic will have expectation 0. Okay, and the variance is Fisher information, basically. Yeah, so that's how we can do the score statistic. All right, that's the fixed effect covariance. And then we can add a random effect. So random effect, we may have some group covariance. Okay, so let's see, called ZI. So these effects, I would say their effects, I would say the values of their effects are not of interest, or they're just too many to estimate. There's just too many to estimate. So therefore, in this case, what do? We can just estimate the variance of those effect values. So the strategy is to estimate their variance and test if the variance is 0. Instead of worrying about each effect size and test if that effect size is 0. So basically, we don't care about beta. We care about beta 1 to beta R, how they are jointly, whether the variance of beta 1 to beta R is 0. Because if the variance is not 0, it means that there must be some differences among beta 1 to beta R. So that will give me the fact that, okay, the groups have some effect. So I think the motivation here is that there are some covariates you must account for to do a good prediction or to have a reasonable model that can fit your data. But you don't want to estimate so many parameters. Therefore, you just estimate those parameters common variance instead of those parameters themselves. That's the intuition. So I would say this whole class will give you this idea. I hope to give you this idea that there's no single model that you might consider, and statistical modeling is very subjective. The subjectivity comes that you can go with a complicated model, you can go with a simpler model. Complicated model will of course fit better to your data, but is it always better? Not necessarily, right? Because the complicated model may not be able to fit a new data set if the new data set have independent variance from independent randomness from your current data set. So that's why I think ultimately it's about signal to noise decomposition. Basically, if your signal is complicated, which is the systematic structure part, if it is complicated, you want to make this part more complicated. For example, we can even go from linear to nonlinear, which we didn't talk about for this part, but it's possible to do that. But if your data has a lot of randomness, so basically it's possible your data has a simple systematic structure, but a big randomness in your random structure, then in that case, fitting an overly complicated model wouldn't be helpful. So at least I think this kind of decomposition is a way to help you think more clearly, what do I assume as the signal in my data? What do I assume as the randomness in my data? That's, I think, the most important thing for us to think about when we do modeling. Okay, so therefore, from my perspective, I wouldn't think the success of the complex models, like the large models nowadays, is it just means a failure of the statistical modeling. I don't think so. I think it's just that for the successful applications like language, the signal to noise ratio is very good in the data, and the signal is complicated. So therefore, we use the large model to model the complicated signal. Well, in some cases, maybe biology, maybe, the genomics, which I'm working on, or maybe social science, maybe sometimes in the data, the noise is so high, right? The signal is basically low compared to the noise. So in that case, you cannot really afford a very complicated systematic structure, or you don't need that. And the more important thing is how would you assume the randomness is in your data, the independent things are in your data. Okay. All right, so I think that's all I want to say. I feel like okay, and also one more thing which I didn't talk about is the GLMM. Okay, generalized linear mixed effect model, just like a generalization of linear mixed model. So if you want to do GLMM, your random covariates will go into the systematic structure. So the systematic structure will have a random component, and then that random effect will again follow its own normal distribution. So that's what people typically do for the GLMM. All right, I think that's all I want to say about the review, which is kind of brief, but I hope to give you a high level understanding of what we have covered. So whenever we have a model, we need to talk about the goodness of fit, right? Whether the model is reasonable. And if the model is reasonable, then we fit the model by some optimization. And also for optimization, we talk about Newton-Raphson Fisher scoring. And with the parameter estimated, then we do inference on the parameter estimate, on the parameter. We use parameter estimates to do inference on the parameter. Yeah. So that's the general idea. And I think this idea is not specific to linear model GLM, but it's general to all statistical modeling if you use the frequentist paradigm. All right, so I think that's all I want to say. So for the remaining time, I would hope to give you some time so you can use this time to fill out the course evaluation. Then you don't have to spend extra time on that. I hope to receive your feedback on this class, and hopefully we will give you, I will say, I can do better next time. And I'll think about what should I improve and what should I cover more. And then for the remaining time, for those of you who have questions, you can stay in the Zoom and answer questions.